Question 8, and we're on with another modelling question. This time we're looking at the cost of a journey in relation to its velocity or its steady speed, v. What we want to start by doing is finding a value of v which minimises the cost of the journey. So I want to differentiate this function with respect to v, so I want to find dc by dv. To do that successfully, I'm just going to rewrite that equation so that it's 1500 v to the power of minus 1 plus 2/11 of v plus 60. Now I can differentiate that with ease, which is going to be minus 1500 v to the power of minus 2 plus 2/11, and then the 60 will annihilate itself. I want to find out where dc by dv is equal to 0, and that's going to indicate that I've got a turning point, so I want to solve 0 is equal to minus 1500 v squared plus 2/11. To do that, I'll just rearrange so that I've got 1500 over v squared, which will be equal to 2/11, and then rearranging that, I'm going to get 750 if I divide by 2 multiplied by 11, which is equal to v squared, and at this point I resort to my calculator to find out that v is going to take the positive value, because we're talking about the steady speed of the vehicle, which rounds to 90.8 kilometers per hour. For the second part of this question, we want to find the minimum cost of the journey. So for part 2, I now want to find that cost. Well, the cost was 1500 divided by v, which I'm now saying is 90.8, plus 2/11 of 90.8 plus 60. Now I've used the exact value from my calculator to get the exact value for this using my answer from the previous question. So I have 90.0, not 90, I have 93.0 or 93 pounds at this point. If we wanted to be nice here, we could say that this is evaluated at v is equal to 90.8, I suppose, and that would look a little bit messy here, but more mathematically accurate. For part B, we're looking to prove that we've found a minimum cost. So to do that, we want to find the second differential. So for part B here, I'm going to find d2c by dv squared. So now I'm going to look up to my answer for part A, and I'm going to differentiate that again, and that's going to give me 3000 v to the power of minus 3. Now if I take d2c by dv squared and I evaluate it at this point where v was 90.8, what I end up with is 3000 divided by 90.8 cubed. Now I don't actually need to go to my calculator at this point to know that I'm going to get here a positive number, and because the second differential is positive, that tells me that I have a minimum cost. Finally, we're to state one limitation for this model. I do not like this question, but I suppose looking at it, what is it really asking us? Well, a limitation of this model is that the model assumes that the lorry is going to be driven at a steady speed of 90 kilometers per hour to work out the best cost for the duration of the journey. So I suppose my answer would be that one limitation of this model is that it assumes that the velocity is fixed, or it assumes that the lorry travels at a constant speed. Throughout the journey. Which would obviously be ridiculous, because when it was travelling through the city it would need to travel at a varied speed and would probably be stopped for some time, so it assumes constant velocity throughout journey, which is not realistic. A better idea may be to take the average speed or something like that, but there we go.